Hello, it's Abdurrahim Babatunde Bubola again for this channel, Noble Apostle Designer. Welcome back to this video on the series that we are working on, which is Advanced Petroleum Refining Aspen HYSYS. So this will be the third video in the series, and the name of the video is Advanced Petroleum Refining Aspen HYSYS Debutanizer, because on this video I'll be working on the Debutanizer. So before I proceed to what I'm going to be doing today, I would like to tell the new viewers, if you are just watching our video for the first time, what we do in Noble Apostle Designer. Although this video is brought to you by Noble Apostle Designer, which is an online firm for students and professionals on chemical process design. So we work on projects such as front-end design, Plan ID, Pan 3D, like what you have seen before I started my class. All those intro section of this video, we work on those projects with people remotely. So you can only submit your project to our website www.nubera.com. We'll be glad to help you and to work on your project. So on today's class, which is the Debutanizer, I've already done the atmospheric distillation column over here, the feeder system or the preheating system, and vacuum distillation column here. So the last video in this course series is the Debutanizer. So I'm going to be setting up the Debutanizer column today. So, and I'll be using the same textbook that I use to set the operation parameters of these absorbers and this distillation column and the vacuum column. So, and this is the textbook here. It's good toward simulation as Aspen HYSYS version 10. That's the title of the textbook. So I'm just using their parameters, you understand, to model my code, but the code that I'm using is different from theirs. So for the Debutanizer, this is the specification for the operating parameter for the Debutanizer column for their refining system. So, and we have the feed preparation, which is like this pump here, this Naphtha pump here. So yeah, it's going to increase the pressure of the Naphtha stream to 250 psig using this pump of 75% adiabatic efficiency, and it's going to there will be a preheater to heat the Naphtha stream to 250 Fahrenheit, and negligible period, that is no period up to the heater. So although I should discuss what's the meaning of the Debutanizer, or like from the name, it's trying to imply the Debutanizer is just to remove the C4 content or C4 lighter, that is butane, to remove butane or lighter. It's mostly to remove, or because Naphtha is mostly used to blend PMS, that is premium motor spirits, petroleum or petrol, sorry. So you don't want to be including a lot of light components in the Naphtha stream, you understand? So that's to make the boiling point range of the Naphtha, so of the PMS, to be narrow, not wide, you understand? So you have to stabilize the Naphtha, but that is removing the low boiling point as LPG. So this can now be sold as another product as liquefied petroleum gas, you understand? So so this Naphtha is distilled. So light component is distilled out of the Naphtha, so you have a stabilized Naphtha here. So once I'm done with the simulation, you'll be able to see more about this, you understand? So right now I'm going to specify these two pumps based on the preparation that I have over here, feed preparation for the Debutanizer column. So the first pump is to increase it to 250 psig. So I'm going to specify the pump, and before I have to specify the efficiency. I think the efficiency is already specified to be 75 by default. So I'm just going to go to the outlet pressure to be 250 psig. So it's going to flash the pump of the temperature of the stream and the duty required by the pump. So then the heater is going to increase the temperature to 250 Fahrenheit and negligible period up. So I'm going to set the period up there to be 0, so that it will not ask me in the, so it will flash the period here to be 50 ppsig. So this place is also 250 Fahrenheit. So the temperature is, so this is the duty for the heater, feed heater to the debutanizer column. Then you have the C4, that is the debutanizer feed here. So then let's start to, because for all the equipment, before you define the unit operation, you must define all the feed stream. And since DC4 feed has been defined, so the next thing is to define the depenizer column. And for others, so the depenizer column is more like is a distillation column. Why, you understand, most of the atmospheric column is reflux absorber column, while the vacuum is an absorber column. You understand? So this one is a distillation column because it's having a boiler and a condenser, and it is a total condenser because all the feed is condensed, all the vapor stream that is going to the condenser is condensed, you understand, to liquid state, and from there you are drawing your reflux and your distillate, you understand. And there is a boiler here, you understand, that is going to boil up some part of the bottom jaw from the last stage, you understand, while the others is taken as stabilized naphtha. Then this is the duty for the reboiler, this is duty for the condenser. So the feed stream to the debutanizer is at stage 22, and the total number of stages for the debutanizer is 45 stages, and the numbering is stopped to the, and that's just this. And so I'll be specifying the period. This is not the, this is just the default period for the space. So I think I should specify the period next. So for the, like, the tray is having 45 stage, then after the period I'll do the efficiency here. Then the period is 150 psig on the condenser, top tray is 150, you understand. So I'm going to be deleting first so as to avoid error. So let me remove this, and so I'll remove this. So for this I'm going to be saying 150 psig, and this is 160 psig. So I think the period has been specified. So the first stage is also going to be having 152. This stage is also going to be having 160. If you check the profile very well, you see it here. This 150 you can see, and this is also having 160. So it will normalize, like this, proportionate the other stages or period, you understand, so that so that they are having equal period drop, you understand. So, and we, oh, it's not period drop, period increase with depth, you understand. So it, because period increases with depth, you understand, decreases with height, you understand. So we have the condenser period and the boiler period, and the period network has been specified. So there is also a side draw stream here, that is the water draw stream. You can see the type is water draw. You can make it to be vapor or liquid here by choosing vapor or liquid stream. Yes, is on the draw stage as a condenser. So it's going to excess water in the system, going to remove it from the condenser, you understand, so that there is no water accumulation in the system, in the distillation column. So then I will do the efficiency. To do the efficiency, you go to the efficiency tab here, this estimate. So because this is just having one group, like it's all the trace 80, so I'm going to do it just manually, not using grouped method, user defined. So you make all the three, because condenser stage is having one efficiency, because efficiency is just going to use to model mixing, that is how the system is in equilibrium. Because if you're having a very efficient stage, it's going to make sure there is perfect mixing of the vapor stream and the liquid stream that is coming to the stage, you understand, so that everything that is leaving the stage is living at equilibrium, you understand. But condenser, there is perfect mixing in the condenser, because it's like a vessel on its own. It's not a stage, you understand. So everything actually condensed in the stage, you understand. And there is no mixing of two phase. It's just one phase, that is vapor phase, that is coming to the condenser, and it's condensed, you understand, to another equilibrium state, which is in liquid state, you understand. So the efficiency for the condenser and the boiler is always one, you understand. But the stages it's not a must that they are one. So they are saying it's 80% efficiency. So I'm going to be putting 80% efficiency for the stage. So I'm going to write in 0.8. That's the fractional instance. So I'm going to skip this video so that not to waste much time. So I'm done with the efficiency. So I'm going to go to the, so let me check the other specification that they have here. So there is no temperature estimate. You understand this feed location. So I'm going to start doing the spec, that is the reflux ratio, because they are giving us the specification for the reflux ratio. You understand? So the reflux ratio is the liquid that is coming, that the reflux divided by the distillate. You understand? So you can specify the reflux ratio. So you can specify the reflux ratio over here. But before I specify it, I want to check. Okay, so this is in molar basis. Let me check if it's the same thing here. Okay, I'm going to make it to be, they mostly specify the reflux ratio in molar basic. So I'm going to make it to be in molar basis, not because although they didn't actually give us value here, but the best is to use the molar basis that they have in here. So the stage here. So we have the reflux based on which liquid you can choose, maybe just vapor and water stream. You understand? So I'm going to specify it to be 1.5. Although this is part of the default from the column, you can still add a lot of spec from it here. You understand? So distillate rate is the rate of the distillate that you're having, and they are giving us to be 5,500 barrel per day here. You understand? So I'm going to be putting that 5,500, but it's going to be in volumetry. This is in molar. So standard ideal volume. So 5,500 barrel per day. So once although sometimes it's automatic, it will just calculate because the degree of freedom is already 0. That is, this is the distillation is needing 2 specification in order to solve for the column. So I'm just going to run it so that I can see the results. So let's see. Okay, it has converged. You can see the green converged sign here or status here. So and this is the iteration equilibrium errors, you understand, and the its spec error. So if below the tolerance is going to converge, you understand. So this is the period profile and the temperature flow, all this kind of thing. So I think once we have converged the simulation, you can see all the unit operation is now blue, that is everything is converged. So the next thing is just to analyze the results and something like that. So I told you about the Debutanizer is remove the light component, and you can see from the performance here. From here you have ethane, propane, H2S, butane, all this kind of component. So all this butane, you are supposed to be seeing it in the LPG, not in the stabilized naphtha. You can see your pentane, your butane, and is in composition. Let's see it in flow, and you have it in flow here. Let's put it in liquid flow. So this is it in barrel per day flow. So this is the amount of butane that you have. Butane, you can see 434.6 barrel per day, and you are taking it out in the LPG stream over here. Where is the LPG? Okay, isobutane, you can see, and not in stabilized, but pentane 2 is taken out as LPG. So from here you can see you're having component of high on petroleum PMS or standard PMS blending points are taken as stabilized naphtha. So you can now use the naphtha to blend your PMS, and you're not going to be seeing. So now you see 0 flow for the LPG and the water stream, water draw. You understand? So that is the meaning of the Debutanizer column. So then you can check the other profile of the Debutanizer column on the reflux ratio, the boil-up ratio, and the flows, and the pressure and the temperature of each stage that is calculated. So the top stage temperature is 320 Fahrenheit, and the bottom stage is okay. The condenser temperature is 220, while the reboiler is 492.5 Fahrenheit, and this is the duty for the reboiler. you have the DT for the condenser here, and the distillates here, the feed stream here, and the stabilized naphtha stream at the bottom here. So this is the feed and product stream something. So you can go to the plot to check some of the properties of the stream, like pressure, temperature. You can fill the graph for the temperature here, make it larger so you see the temperature profile. I think this is supposed to be in the feed stream, because that's how you're having temperature like that. So feed stage, sorry, let's see, is it in the feed stage? Okay, it is. You can see it is a feed stage. So the temperature of the feed actually affects the tail temperature. You understand, like the quality, the feed quality or something. So we have the flows. So from the flows, you see the flow of the stream from each stage, the liquid flow and the vapor flow from each stage. So, and okay, there is mass flow here, there is molar flow, and there is liquid flow. Okay, the first liquid flow is just the liquid flow based on the specific volume, while the idea is based on calculating the density of the stream, but it's going to be at the standard pressure and temperature of the standard pressure and temperature, like STP 25 degree and the at 25 degree, and the bubble point pressure of that stream composition, you understand. So that will give you the volume, that standard the liquid volume, and this is the actual volume of the based on the density calculation of the at the temperature and pressure of the stream. This is also at the temperature and pressure of the stream. Yes, and so that's all the difference. And we have the light liquid. If you're having like your three-phase distillation column, and you want to plot two liquid phase, that is the organic and the aqueous phase, you understand. So you can separate your liquid phase into two. So you make one to be light liquid while the other one is in heavy liquid, you understand. So this is the meaning. So then you can get other kind of plots. So for example, you can do petroleum boiling point analysis of the stream that you have. So you can set it up here, like okay, you do the let's okay, you can do for single stage, maybe for the condenser. So like the logic is like, or any stream that is coming out of any unit operation, you have the same composition, the same property of that unit operation, or of the content of that unit operation. So, or if you are plotting the true boiling point data for the condenser, that means this stream should have that same true boiling point. You understand? So instead of attaching it to the stream, you attach it to the unit operation itself. So now I'm selecting condenser. I can plot the true boiling point of condenser here, and which phase do I want to plot? It's in liquid phase, not in vapor phase. So I'll just plot the liquid phase or true boiling point. So you have this is the true boiling point of the liquid phase. You can plot this one too and compare the result of each boiling point type, you understand. So you can choose for multi-phase, you understand. Select the type that you want to put true boiling point, then choose different kind of stage. You can see the boiling, these are the light components. As you am adding to it, the boiling point is increasing. Look at this one. The next one should be on top, you understand. If I want to choose the last stage, you should be having higher boiling point, that is as higher temperature. So for example, 45, you can see the boiling point, and the boiler will be on top of this, you understand. Then this one will be at the bottom, you understand. That's how the boiling point of each stage of each component. So the component that you want to take out should be taken from where you want, the stage that you want to take it out from, you understand. So that's the result of the boiling point. So and it's a lot of things. Like once you are done with your simulation, the next thing is to analyze your results. There are a lot of tools in Aspen HYSYS that you can use to check and compare your results, your model, you understand, and analyze your results, you understand. So even if you don't want to do the boiling points in calculation within Aspen this column, distillation column, you can still go to each stream and do some petroleum analysis for each stream. For example, I will do petroleum analysis on this kerosene stream and check its petroleum properties by going to the petroleum assay here, you understand, because I'm using petroleum assay. And for example, I've already done the petroleum acid, like choose this petroleum acid property of this kerosene stream, and it is now showing me okay. You understand? So I can check my results here. That is the true boiling point of the cut volume from 22% to all these 99% final boiling point. So this is the initial boiling point of the kerosene stream. So this is the true boiling point. Two boiling points in volume or volume basis. This one is a mass basis. This is another boiling points curve. You understand? Then you check properties here. This is a plot of the true boiling points data. Then you can check other properties over here, like okay, let's check the table for the properties first. So this is the table, the volume cut percent, and you can make it in mass percent. You understand? True boiling point, specific gravity, API gravity, all the petroleum properties, freeze point, flash points, aspartame contents, and where's after? Okay, we have the sulfur content and the capital sulfur contents very low. You understand? Calculated mercaptan or estimated mercaptan viscosity data of the you know the more data you use to classify your crude, the more these data are more accurate. You understand? So if you didn't characterize your crude very well, you won't be getting a very accurate result. You understand? So you have the heating value of the fuel. You understand? So these are a lot of things that you can use to make a decision in your process. You understand? So I don't know. I think okay, aspartame content. You can see aspartame content here of the kerosene, and this is the plot for everything. You can check the plot for okay for pour points here. Okay, for all the cut points and the sulfur contents of the cuts. You understand? Then there's a lot of properties that you can plot, and the acidity of the cuts and the aspartame contents of the cuts. So you see it can be in normal boiling point or in volume fraction. If it's in volume fraction, you can see it. That means some points are having a close boiling range. All this they're having a close boiling range, you understand? And they are not in the cuts. You understand? This is in cuts, volume cuts and mass cut and mole cuts. So with percent, ppm, just you understand, just going to change it. So you have a lot of things that you can work on. You understand? So that's on petroleum acid. If I try to use the boiling points here, you know I've already done it with the column. It's going to return error because I characterize the crude with petroleum acid, not oil manager. You understand? So that's the thing. So you can do boiling point analysis for any stream in Aspen HYSYS. You understand? So then if you are done with it, you can see export the result of your simulation to maybe Excel format so that you can use it in another in your study into maybe you want to send it to your supervisor or your boss. You understand? Or you want to do some other calculation. You understand? Maybe management calculation that is not related to chemical engineering. You understand? So you can just send it to Excel by creating a report here, summary of the flow sheet. So you use templates, Excel temperatures. You understand? You just browse for templates here. So you have each work profile, HYSYS templates. Then let's just use petroleum refining workbook. You understand? That's because we are doing petroleum refining. So all the properties that is going to be used in this Excel workbook is going to be related to petroleum system. You understand? So once I've created the templates, so I will create the reports here. So it should take some time, so let's wait for it. Okay, so it has created. So you have the listing of all your energy stream all the energy stream that we use, the heat and the flow duty. So you have the composition here. So you see the composition of all these stream here. You can see from the crude oil stream, one stream, the water stream, the one wet stream. It can see you see all the everything there. So you can make reference to all these values now. So you have all the values in the Excel sheet. So you have the material stream properties here, and even you have the the boiling point properties of each of the stream, the API gravity, you can see the petroleum properties, API petroleum properties, specific gravity. You have the molar enthalpy, the heat flow, standard liquid volume heat flow, the mass flow, molar flow, and the vapor fraction. Then you have all these petroleum properties. You have it copied for each stream. The vapor pressure, real vapor pressure. This is also very important for petroleum system. You understand? We have the workbook summary. So this is the summary here. So that's that on the copying, like exporting, like creating workbook or Excel workbook reports in your simulation. So then you can do the last thing. The last thing I want to do is just to show you another mini workbook in an Aspen HYSYS that you can still use to check to arrange your simulation results. You understand? So you can go to workbook here. You see a lot of properties of the stream. So you have the same thing that you have in Excel. You understand? You can still see it in your Aspen HYSYS. So this is the Aspen HYSYS workbook. So you have the composition tab, the energy tab, and the unit operation tab. You can add any properties from to the workbook from your manually. You understand? Maybe you want to do a custom workbook, not the default one. You understand? You can add any properties by going to setup. You understand? Maybe it's just material stream property that you want to add. You can see this is the other tab. This is the tab that you can add. You can add a new tab. You understand? I put a new data, and you can add another data to the tab where you have. So for example, I'm going to add, okay, I'm going to have something like critical pressure to this stream. So I'm going to add a critical pressure property. So I'm going to look for critical pressure here. Okay, it's not okay. Not there. So let's just add this molar volume instead of critical pressure. It's supposed to be in property of the stream. Maybe because it's a thermodynamic property, or it's just for components, not okay. Critical pressure is just for components, not for the stream. You understand? So you have this. So I've added the molar volume. Okay, where is the molar volume supposed to be? Okay, you have the molar volume. I can reorder it to be on top or something. So if I want to reorder it, I'll just make it to be on top. You can even add some, you understand, and put it later. Okay, let me put it after prayer. Okay, so we have this and you see the molar volume. Now you can see the molar volume and the units of each stream in the simulation. So this is for the, you see, for the second, this is for the second row, atmosphere. So this is the molar volume for all the, most of these things are the same stream, and this for the naphtha stream and the residue stream. So that's that on the workbook in Aspen HYSYS. So thank you for watching and thank you for your time. So stay tuned to our channel and always give us feedback and share our content to your friends and colleagues. You understand? Before you end this video, don't forget to like and subscribe if you haven't subscribed. You understand? So that's the thing that will encourage us to do more on this video and also give you more exclusive content on Nubia Preset Designer. So thank you for watching.